All right, welcome to the Explainer. Today we're throwing three absolute titans of computer science into the ring for a showdown: merge sort, quick sort, and heap sort. Now, if you're a developer, you've definitely heard these names. But the real question is, do you actually know which one to bet on when performance really matters? So we're going to frame this whole thing as a competition. In the world of sorting, there are a ton of contenders, but these are the heavyweights. And our goal today is simple: figure out which one can truly be called the best. So let's just get right to it. If you had to pick one, just one, for every sorting job you'd ever have, who would you choose? Would it be the super reliable and consistent merge sort, the legendary, often blazing fast quick sort, or maybe the incredibly memory-efficient heap sort? Now, you might think there's a clear winner just based on what the textbooks say, but I'm telling you, the real-world champion isn't always who you'd expect. So stick around, because the answer is way more nuanced and, honestly, a lot more interesting than you might think. Okay, so before we can crown a winner, we need to actually meet our contenders. Let's break down their core strategies, what we're going to call their unique fighting styles. First up, in the blue corner, we have merge sort. Its strategy is pure divide and conquer. It takes a big, messy list, splits it in half, then splits those halves in half, over and over, until it's just a bunch of lists with one item each. From there, it methodically merges them all back together. The two key words here are divide and conquer, and, really important, stable. We'll circle back to why that matters so much later. To make that concrete, just imagine a totally disorganized stack of books. Merge sort is like tearing that stack down into individual pages. A single page is, by definition, already sorted, right? So you just start merging them back together, two by two, in the right order, until you've rebuilt one single, perfectly sorted stack. It's incredibly methodical. Next up, our challenger, quick sort. Now, it's also a divide and conquer algorithm, but its approach is totally different. It picks one element from the list, calls it the pivot, and then shuffles everything else around it. All the smaller items get tossed to the left, and all the bigger items get tossed to the right. Then it just does that exact same thing to those two new, smaller lists. Sticking with our book analogy, this is like you just grab one book off the shelf to be your reference point, your pivot. You then make two new piles. All the books that come before it alphabetically go on one side, and all the books that come after it go on the other. And you just keep repeating that little trick on the smaller and smaller piles until, suddenly, everything's in order. And our final contender, heap sort, brings a completely unique strategy to the fight. It starts by organizing the entire list into this special tree-like structure called a max heap. Now, in a max heap, there's one simple rule: every parent has to be larger than its children. And this one rule brilliantly guarantees that the biggest, baddest element in the entire list is always sitting right there at the top. Think of it like a King of the Hill tournament. All the books are put into a bracket where the heaviest or largest book is guaranteed to win and become the champion at the top. So you take that champion, put it at the very end of your sorted shelf, and then you run the tournament again to find the next champion from all the remaining books. You just keep doing that until the shelf is full and perfectly sorted. All right, introductions are over. We know their styles, now let's put them head to head in the arena. We're going to judge them on the two things that matter most for any algorithm: how fast do they run, and how much memory do they chew up. Round one is all about speed, what we call time complexity. And check out the consistency on the left. Merge sort and heap sort are like marathon runners. They are steady, they are predictable, and they will always give you a solid n log n performance no matter what you throw at them. Quick sort, though, it's the sprinter. On average, it's also n log n, and usually faster in the real world, but it has this terrifying worst case of n squared, which means if you give it just the right or wrong data, it could slow to an absolute crawl. Okay, now for round two, memory usage, or space complexity. And this is where the tables just completely turn. Merge sort, for all its beautiful consistency, is a memory hog. It needs a whole extra copy of the array to do its work. But look at the other two. Heap sort is the absolute champion of efficiency, using a tiny, constant amount of extra space. It's incredible. And quick sort is also super lean, using just a little bit of space to keep track of its partitions. So let's bring it all together on a final scorecard. This table sums up everything we've talked about, but I want you to focus your eyes on that very last column, stable. So what does that mean? A stable sort means that if you have two elements that are equal, like say two number 5s in your list, their original order is perfectly preserved after the sort. This can be absolutely critical when you're sorting complex objects. And as you can see, of our three contenders, merge sort is the only one that guarantees it.
So, looking at that table, you might be leaning towards merge sort or heap sort. They seem like the safe, predictable choice, right? Well, now we get to the surprising part. We're about to debunk a very common myth and reveal why the best theoretical stats don't always win you the prize in the real world.
This is the big one. The fear that gets drilled into every computer science student, that dreaded n-squared worst case. It makes quicksort sound like a reckless gamble. I mean, why would you ever risk a catastrophic slowdown like that? Well, here's the secret. In practice, that worst-case scenario is so incredibly rare, it's almost a myth. Modern versions of quicksort have really clever ways to avoid it. The monster that everyone's afraid of is effectively trapped in a bottle. It almost never gets out in the real world. So why does quicksort usually win? Well, a few huge reasons. First, modern implementations use randomized pivots, which basically makes hitting that worst-case scenario a statistical impossibility. But second, and this is the real kicker, it has fantastic cache locality. All that means is it works on chunks of memory that are physically close together, which is exactly how modern CPUs are built to work fast. It's like having all your tools right next to you instead of having to run across the room for every single one. That raw efficiency makes it the undisputed race car of in-memory sorting. Okay, so what does all of this mean for you practically? Let's boil it all down into an actionable playbook that you can use, especially when you're sitting in a technical interview and you need to explain your choice of algorithm. So here it is, your interview playbook. It's just 3 simple questions. First, ask yourself, do I need stability? If the answer is yes, the choice is made for you. It's merge sort. End of story. Second, am I completely forbidden from using any extra memory? If you're in that rare situation, heap sort is your safest bet. But for the vast majority of general-purpose sorting jobs, when the question is just, what is the fastest way to sort this thing in memory? The answer is almost always quicksort. That's your champion. So, it turns out the real winner isn't the algorithm with the most perfect report card, but the one with the best real-world rubber-meets-the-road performance. And in this showdown, for most cases, quicksort takes the crown. You've got the theory down. You know the what and the why. So the only question left is, are you ready to code it? Thanks for watching.